Hello, my name is Ivo and I am doing research into Nikola Tesla's impulse electricity. In my latest videos I have showed you the ability to switch MOSFETs in series. But I ran into problems due to the SMD conversion PCB. It created a shortcut which limited the high voltage impulses. Therefore I designed new SMD conversion PCBs that can withstand much higher voltages. This makes it possible to produce even higher voltage impulses. Let's take a look. First, let me give you a small update on what I'm working on, what the intention is. The Chinese New Year delayed the delivery of my newly designed conversion PCBs, so I had time to read some of the lectures and patents of Nikola Tesla again. In Nikola Tesla's lecture at Columbia College, May 20th, 1891, he clearly states he used high voltage electrostatic induction. Until now, I have been testing to see if I could get it to work with relatively low voltages of several hundred volts. But after seeing the results of the previous videos, I came to the conclusion that Tesla effects only barely start around 600 volts. And it is clear that I need much higher voltages to get better results. That is one of the reasons why I want to produce higher voltage impulses. But not only that, I also concluded I need to use much higher voltage DC offsets again to create the electrostatic condition that is needed to interact with the surrounding ether. The radiant half-bridge circuit PCBs that I shared in a previous video, they can not only be used for a half-bridge circuit, they can also be used for the radiant power circuit that I published in April 2019. We can use this to switch the 2 or even 4 MOSFETs in series to get really high voltage impulses and very high voltage DC offsets. The idea I'm now working on is to use 2 pancake coils as capacitor plates. I will give one plate a high voltage DC offset, and this will charge up the dielectric field between the 2 plate coils. One of the plate coils is made series resonant and it is impulsed, just like the radiant power circuit that I published in April 2019. Single polarity. This creates a quick implosion of the dielectric field between the plate coils. This implosion creates a vacuum that is filled up by the surrounding volume of ambient ether around the coils. And this inflow of current of ether has inertia and creates momentum, which can be used. This process also explains the current amplification that I witnessed in the experiments which I showed in the radiant half-bridge circuit producing triangle waves video of November 2020. To test this, I first need to be able to produce these high voltage impulses. And that is why I designed new PCBs for the gate driver ICs that can handle much higher voltages. I will now show you how I soldered the SMD gate driver IC to the conversion PCB that I designed. Let's take a look. I have got here a DIP 8 socket. I'll put a measure underneath it. This is 1 centimeter between the 7 and the 8, and the stripes represent 1 millimeter. So you can see we are working under a microscope. This is the socket I use on my half-bridge PCB, and I use it so that I can use a
conversion PCB with sockets, because my gate driver IC is really tiny. It is a SMD part that fits on this. And by doing it this way, if I break a gate driver IC, I can easily replace it. But this conversion PCB that can be found in many stores online has a setback. As you can see, there are connections in between, and these provide a shortcut for high voltages, because these 4 contacts and these 4 contacts should be isolated from each other, and they are not, and that caused a problem with my setup. So instead of using this one, I designed my own, which is this one. It's the first prototype and it already looks pretty good. Here's the IC. It fits on the pads, and this way I can work with it, because now the pads are isolated. There is 3 millimeters between those pads, and I could even stretch it a little bit further to 3.5 millimeters, but I probably will advance this to optical isolation of the signal. So I'm gonna put this on here, and to do this I am going to make some epoxy, and the epoxy I will put on here. I will stick the IC on top of the epoxy and then solder it together, and this way I will have a very high voltage separation between the input side of the chip and the output side of the chip, because here are the high voltage impulses and I want to generate a few thousand volts of them, and here is the ground level of the logic, and that should be isolated. So 3 millimeters isn't much, but it is a lot more than I had before, like this. I'm first gonna solder in the pins so I can fixate this all. These are the pins, and this will be the connection between the socket and the PCB. So this part is a little bit shorter, but it's a little bit thicker, and it seems to have a better fit for these sockets. Now there's a little indentation on the top here, and that indicates where the 1 point is, and you can see it here, it's the same. So I'm gonna put this on the pins, readjust the lens of the microscope. There we are. I'm gonna solder this together, then I'll have a PCB with pins and it's all fixated. It's nice. This is a special SMD pin. It's really tiny. Doesn't look tiny on screen, but it is very tiny. And I'm using basic solder. This is the easy part. This is through-hole technology. This is what I'm accustomed to, and I would like to continue to use this, but in the future I probably will be forced to use SMD technology, as some parts are just not available anymore with through-hole technology. Like the gate driver IC that I'm using. It's a great device, but it isn't available in through-hole technology, THT. It's only available as SMD, surface mount technology, or whatever that stands for. So now I can go and make some epoxy to glue that IC onto here, like so. Now I'm going to make some epoxy. Okay, I've got a little scale here, and I've got my resin here. It's 1 to 2 parts of hardener, 1 part of epoxy basis to 2 parts of resin hardener. It's a slow hardener, so that's nice. I will turn this on. I only need a little very tiny little bit of epoxy. So I'll probably end up with much too much. Yeah, this is gonna be messy if I do it like this. I don't like it. It's poisonous stuff. So I got my little scale here, put on 0, and I'm gonna need one little bit. Let's see, how much is this? It doesn't weigh what is going on. Okay. This is not a good scale for this. I don't understand. They always used great, work great. Okay, put a little bit more in. 0.2. That's the epoxy basis. Close up again because this is all poisonous stuff. Yeah, and I take a different pipette. Here is the hardener. It's a slow hardener, which gives me a lot of time. I'm gonna use twice as much as this. This is right now 0.2. So I'm going to add it to 0.6. That's already too much. And the scale turns off. Wow, great. Yeah, it's one of these days. So I had a little bit too much, 10 units. So I'm gonna take a little bit. What is still in here? No, there's nothing in here. Turn it on again. And just a little bit extra. Just a little bit. 1, 2, 3 drops. That should do it. Okay. Now I'm gonna mix it up with a little spatula. Now it stays on, you see? It's a stupid device. So mix it up. It's just a little bit of epoxy, but it's way too much for what I intend to do. In the end I will make 4 of these, but I will only show the process of one of these conversion PCBs. So mixing it, and now I'm gonna use a little bit of it to get the IC on top of the PCB. Let's go back to the microscope again. Now I need to get a little bit of the epoxy in between those parts. So I'm just gonna use my wooden spatula and put a little bit in between. Let's see if that works. Yeah, perfect. There's a little bit of an air bubble, but yeah, that's good enough. So now I am going to get my SMD K-driver IC and put it on top. As you can see, it already starts dripping to the side, which is not that good because I need to solder it already. Yeah, this is going to be a problem because now the soldering pad on the right is covered with epoxy. That's bad because I need a connection there. I'm just gonna try to solder it. Yeah, I'm just gonna give it a shot, see what happens. Let's see if I can fixate the SMD first in that corner. It's a little bit tricky. I'm gonna put some solder. Yeah. Okay, I believe it's fixated now. This is really crude. I'm not perfect at SMD soldering, and I'd rather not be perfect at it because that would mean I would solder a lot of SMD, and I don't want to solder any SMD. It's for robots, it's not for humans. So let's see what happens when I heat this up and put some solder there. It seems that it is working, so that's cool. Clean my tip and keep cleaning that tip because I use much too much. This is really tricky. I'm trying to get it underneath the pad. This is very messy. As you can see, the epoxy is messing everything up. This was a bad idea. Very bad idea. I see the solder is flowing now. So it seems it is making contact. Let's do it one more time. Far from ideal, this. I don't like this at all, but I'm doing my best. It does work. I do believe I'm really soldering it. Due to the heat, the epoxy is removed. Of course, this is very tricky because epoxy is toxic, and I'm heating it up in very small amounts. And this is a bridge that shouldn't be there, so I should remove it again. I've got some wick for that, which is copper braid. Let's use that to soak it up. Come on. Soak it up. You can do it. Soak it. Yeah, there you go. Soak it all in. And it's gone. Now it's in the copper. Yep, good enough. Okay. It's looking very, 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 very ugly. Gonna give this one a little heat. This one also. This one. Clean up my tip. Yeah, this looks good enough on me right now. Remove this blob of lead, because I do solder with lead. Okay, I'm gonna remove it from the socket, and now I'm gonna swap it around so I can work on the other side and put it back in socket again, so I can use it, work with it. Let's check it. How does this look? Let's it does look like it's soldered. I'm first gonna solder the other side, which also has some epoxy resin on it, I believe, and see how that happens. It's only 3 parts. Yeah, epoxy is absolutely present there. I'm just gonna heat it up, and yeah, it flows. So I do like it. I think it is working. Got a little bit much of the solder here. Oh, I'll clean up my tip. Clean tip takes the solder away. Yeah. Okay, let's do that here. same. Yeah, it is flowing. Alright. This bridge isn't bad. I can leave that because it's the right pin. And then another one here. Let's angle the... Yeah. It is working. This is the first time that I did it like this, by the way. So you always learn from these little projects. The next time will probably be even easier. Okay. I have a little brush here that I'm gonna use. Let's see if I can get rid of that doesn't work at all. Whatever. Okay, it looks like a mess, but actually I think it is working. I'm gonna test the connections with my multimeter that beeps when I have a connection. Let's see, put it on the right setting. Maybe you can hear that beeping. Let's see. Yep, that's good. Well, this is good because here nothing is happening, so... Oh, there it is. There it is. Everything works. Yep, beep. Okay, here is an epoxy layer, so I should probably penetrate that layer. Yeah. These two I have to scrape down with some knife to scratch through that epoxy resin to be able to test it. It's really messy. Yeah, well, it will have to do. I don't want to make a lot of metal scrapings. I did get a beep, but that was a short. Oh, there it is. Yeah, I do believe it's working. And this one also works. It's good enough for me. It's really ugly. I'm gonna get a little bit more of epoxy resin. Let's see. It's still liquid. Yes, it's still liquid. That's nice. I'm just gonna rub it over the contacts, because now it's all fine. So now it should be very well isolated once it is set. Yeah, got an air bubble there. It's not ideal, but I think it won't matter. So I'm gonna leave it like this. I'm gonna set it away, leave it to dry, and then I'm gonna test it. Because first I'm gonna make another 3 of these, and hopefully they will become better and better and better. Because this was the first one, and usually that isn't the best one. Okay.
Now it is time to start testing these new PCBs. After these have been tested, I can proceed to make a high voltage capacitor with the 2 plate coils. This information is all open source and it is free to be used by all. No patents can be applied. If you want to support my research, you can give a donation via the PayPal link that can be found in the video description below. If you enjoyed this video, please hit the like button and subscribe if you not already have done that. Hit the notification bell for a notice of my future videos, and please share this video with those that you think will like this information also. That's it for now. Thank you for watching and see you next time.